Welcome back to the lecture series of semiconductor devices and overview. Last time we have talked about what are semiconductors, the central concepts of quantum theory, Schrodinger equation, solution to the Schrodinger equation, particle in a box problem, and finally the hydrogen atom problem. We have also talked about how the concept of conduction band and valence band arises. Today, based on that central concept, that is conduction band and valence band, we will be talking about the three types of materials that we have in hand. We have metals which are very good conductors. For them, the conduction band and the valence band overlap. We have insulators which are bad conductors. We have a large forbidden energy gap between the conduction and the valence band of the insulators, and semiconductor lies in between them, where we have a moderate amount of energy gap in between the conduction and the valence band. The valence band is completely filled, the conduction band is completely empty for starting. Now we come to the concept of direct and indirect band gap materials. As we have already mentioned that our dispersion relation, EK relation, is a function of K. Now if the uppermost point of the valence band and the lowermost point of the conduction band occur for the same value of K, it is a direct band gap semiconductor. Like this is EC and this is EV. They are occurring for the same value of K. If it is otherwise, this is say EC and this is EV, then it is an indirect band gap semiconductor. Now, semiconductors are very flexible. Say we are taking a compound aluminium gallium arsenide. Proportion of aluminium is denoted by X. Gallium is denoted by 1 minus X. Initially, when we are starting with X is equals to 0, so we don't have any aluminium, but we have gallium arsenide. That is a direct band gap semiconductor, band gap being 1.43 electron volt. Then when we gradually proceed increasing the value of X and X becomes finally 1, then we have aluminium arsenide, which is an indirect band gap semiconductor. Therefore, a transition from direct to indirect band gap semiconductor has occurred. Again, we can start with gallium arsenide phosphide from X equals to 0 to X equals to 1. Gallium arsenide will be there for X equals to 0, and for X equals to 1 we will be having gallium phosphide, which corresponds to the green level of energy, having 2.3 electron volt. Next we shall introduce the concepts of electrons and holes, the two most important concepts of semiconductor theory. Now we have at T equals to 0 Kelvin, we have the completely filled valence band and the completely empty conduction band. When T is greater than 0 Kelvin, some of the electrons are leaving holes behind in the valence band, that is, the electron is not present, they are being raised to the conduction band. This distribution of electrons and holes will be perfectly symmetric unless and until an external force has been applied. On the application of an external force, this distribution will become asymmetric, as has been shown over here. Next, we will introduce the concept of electron flow. What is current density is equals to Q, the electronic charge, N, the concentration of electrons, and Vd, the drift velocity of electrons. Now, assuming there are n number of electrons, we are summing up all their velocities. And here we are substituting the electronic charge to be minus E. Electron has negative charge. This Vi is the drift velocity of the ith carrier. Now, inside an atom, when there exists an electron, apart from the external force due to the applied voltage or electric field, it is also facing some kind of internal force, a repulsion from the other electrons, an attraction from the nucleus. Therefore, two types of forces, one is F external, one is F internal. Both the forces are resulting into a motion of the electron, this being the actual mass of the electron and this the acceleration. But it is very difficult to measure these internal forces. Therefore, accounting for the internal forces, we assume a quantity called the effective mass of the electron in that material. This effective mass multiplied by the acceleration gives us only the external force. Therefore, we have taken care of the internal forces through the effective mass, which differs from materials to materials. Next, the electron will now behave as if it is a free electron, only its original mass will be replaced by the effective mass. So the dispersion relation we have E equals to h cut square k square by 2 m star, and from that we obtain 1 by m star is equals to 1 by h cut square d2e dk2. Now what? What is the relation between E and k? See, this is the relation between E and k, the conduction band structure. So E minus EC, EC being the lowermost point of the conduction band, is equals to C1 k square. It looks like a parabola, and since E is greater than EC, C1 will always be positive. Therefore, what will be the value of d2e dk2? It will be 2C1, and C1 is positive. Therefore, what is the value of 1 by m star? 2C1 by h cut square. Therefore, m star is positive. That means the motion of electron occurs in a direction, is applied electric field, thus motion of electrons is in opposite direction to the field. So is this clear why the motion of electrons is in opposite direction to the electric field? Next we come to the concept of holes. When the valence band is full, breaking of covalent bands will gradually start. Now the current density can be expressed as this in terms of the field state. We can again express it in terms of the total states minus the empty states. So this will naturally boil down to 0, and this will be equal to the empty states portion. Now again the parabola for the valence band, it is bent downwards. Therefore minus C2 k square and E minus EV. What is E? E is the energy at any point inside the valence band, and this is the highest energy of the valence band. Therefore E is less than EV, therefore C2 is positive. Again by similar logic we can deduce that m star comes out to be negative. Thus we have finally come out to the concept of a particle, charged particle, having the charge of an electron but it has negative mass. Now how will we substitute for this? We will think that we have a particle which has a positive mass but it corresponds to an empty state. So this is the state being empty, there being an absence of electron. This is known as hole. Thank you.